List the potential rational zeros of the polynomial function. Do not attempt to find the zeros. We're trying to find the potential rational zeros of f of x equals 2x to the fourth minus 4x cubed plus x squared minus x plus 1. We're going to find these potential rational zeros using the rational zeros theorem. With the rational zeros theorem, we need to have a polynomial function which has integers as the coefficients. And the rational zeros will be in fraction form p over q. And what we see here is that p must be a factor of a naught, and a naught is our constant term, which in our example is 1. Q must be a factor of a sub n, which is our coefficient of our leading term. For this function is 2. So we can form the potential rational zeros by finding the factors of p and finding the factors of q and forming this rational expression from those factors. So let's first find out what the factors of p and q are. So p is a factor of a naught, so p will be a factor of 1. The factors of 1 are plus and minus 1. And then q will be the factors of our leading term, which is 2. The factors of q are plus and minus 1 and plus and minus 2. So our potential rational zeros will be of the form p over q. And so they could be plus and minus 1 over plus and minus 1, or plus and minus 1 over plus and minus 2. We'll reduce each one of these to get plus and minus 1 and plus and minus 1/2. So the potential rational zeros for this polynomial function are positive and negative 1 and positive and negative 1/2. For the following, find the real zeros of f. Use the real zeros to factor f. Our given function is f of x equals 2x cubed minus 4x squared plus 10x plus 20. So I notice that there is a common factor between these terms, so I'm going to start by factoring out the 2, and this is going to make it a little bit easier for me to work with the numbers since they'll be a little bit smaller. So I'm factoring out a 2, and that leaves x cubed minus 2x squared minus 5x plus 10. And now I'll use the rational zeros theorem. P must be a factor of a naught, and q must be a factor of a sub n. So I need to find the factors of p and q. The factors of p are plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10. And q is 1, so the factors of q are plus and minus 1. So this leads me to say that the potential rational zeros of this polynomial function are going to be p over q. So I'll take each p and put it over q, plus and minus 1 over plus and minus 1, plus and minus 2 over plus and minus 1, plus and minus 5 over plus and minus 1, and plus and minus 10 over plus and minus 1. This gives those potential rational zeros to be plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. This gives me a short list of values to check to see if I have any rational zeros. So I'm going to use my calculator to help me go through this list. And what I'm going to do is use the remainder theorem and the factor theorem to help me identify which one of these values on the list is the rational zero, if we have any. So in the calculator, I'm going to type the function into the y equals menu. I've lost my mouse. All right, there it is. So in that y equals menu, I'll type the function, and I'm going to type the reduced function just so the numbers are a little bit smaller. We've got x cubed minus 2x minus 5x plus 10. And I'm going to go into table set, which is in blue above window, so I'll hit second window. And I want to turn my table into ask mode so that I can enter these potential rational zeros in. So now I'll go into the table, which is in blue above graph, and I'm going to type in these potential rational zeros. And as I said earlier, I'm using the remainder theorem and the factor theorem. If we get a remainder of 0, that means that we have a factor of the polynomial and also a 0 of the polynomial. So I'm looking for, in the y column, to have a 0, which would mean a remainder of 0, and that I've identified a 0 and a factor of the polynomial. So let's type positive 1. We see a y value of 4, so we don't have a 0. Negative 1 is a y value of 16, so our remainder is 16 and we don't have a 0 there. Positive 2 gives 4, and that's not a 0. Negative 2, no. 5 and negative 5, 10 and negative 10. Okay, so none of those seem to be working, so let me just double check that I typed my equation in correctly, and I can see that I made a mistake. I typed x cubed minus 2x, and it should have been 2x squared. So let's make that correction. Let me insert the squared there. And let's go back to my table. And now looking at the table, you can see for an x value of 2, we have a y value of 0. And that means that we have a remainder of 0 at 2, a 0 of the function at 2, and we now have identified x minus 2 as a factor of this polynomial. So we now have a rational 0, which is 2, and we know that this polynomial has a factor of x minus 2. So I'm going to use synthetic division to reduce this polynomial more. So I'll use that 0 of 2, and I'll use the coefficients on this polynomial. The coefficient on the cubed term is 1. On the x squared term is negative 2. On the x term we have negative 5, and the constant is 0. And with synthetic division, I'll carry down that first term, multiply 2 times 1 to get 2. Add these two numbers together, give 0. 2 times 0 is 0. Negative 5 plus 0 is 5. 2 times negative 5 is negative 10. And 10 plus negative 10 is 0. Now, since we reduced our polynomial by a linear factor, we can now write down the reduced polynomial. So a cubic reduced by a linear will become a squared. So we have x squared plus 0x minus 5, which is the same thing as x squared minus 5. So I can rewrite my polynomial. So remember we had the original polynomial, 2x cubed minus 4x squared minus 10x plus 20. We factored out a 2 to get 2 times x cubed minus 2x squared minus 5x plus 10. And then we factored out x minus 2. That was the rational 0 that we identified. And now we're left with x squared minus 5. We can continue continue by finding the zeros of this. We'll set our polynomial equal to 0. And we set x minus 2 equals 0, x squared minus 5 equals 0. So x minus 2 solves to be x equals 2. Here I'll add 5 on both sides and get x squared equals 5. Square root both sides to give x equals plus or minus square root of 5. So we've identified the other two zeros to be positive square root of 5 and negative square root of 5. And what I'd like to do is to continue to factor this polynomial one more time, now that we know the other two zeros. So we can write this polynomial as 2 times x minus 2 times x plus square root of 5 times x minus square root of 5. And so we have now identified all of the zeros and have factored that polynomial completely. Use the intermediate value theorem to show the following has a 0 in the given interval. Approximate the 0 correct to 2 decimal places. The polynomial function we're working with is f of x equals 3x cubed plus 9x squared minus 9x plus 9. And we want to show that it has a 0 on the interval from -4 to -3. I've written out the intermediate value theorem here. Let f denote a continuous function. If a is less than b, and if f of a and f of b are of opposite signs, then f has at least one 0 between a and b. So in order to prove that there is a 0 on this interval from -4 to -3, we need to show that the y values at those points have opposite signs. So I'm going to use my calculator to help me show this. So I'll type into the y equals menu the function that we're working with. That's 3x cubed plus 9x squared minus 9x plus 9. And I'm going to go to the table. And right now my table is in ask mode, so I'm going to clear out these values that are here. I need to do that by deleting. I think I can go to the top of the list. No, maybe not. I just have to delete them one by one. And I'm going to type in -4 and -3. Okay, so these are the y values at these points. The y value at -4 is -3, and the y value at -3 is 36. So f at -4 is -3, and f at -3 is 36. And so you can see that f of -4 and f of -3 have opposite signs. So because f is a polynomial and is a continuous function, and we have shown that the y values have opposite signs, there must be a 0 between -4 and -3. So now we want to narrow down what that 0 is. So once again, I'm going to use my graphing calculator, and this time I'm going to use the table menu in just a little bit different way. So I'm going to go to Table Set. And this time I'm going to go in Auto mode instead of Ask. So let me switch this to Auto. And I want to start my table at -4 because that's my smaller x value. And I want my change in the table values to be 0.1. So that means that it will auto increment up by 0.1. So let's take a look at what the table looks like. All right, so let me go back and double check that I've done that right. Okay, so I have it in auto, and let's go to the table. Okay, so I've got it starting at -4.5. I want it to start at -4 and increment by 0.1. Okay, so there we go. Let me get a screenshot of this so we can take a closer look at it. So here's our screenshot. And once again, I want to use the intermediate value theorem. The intermediate value theorem says that when we have a change in the signs, we can identify that the 0 is between those two values. So we're looking at the y values here, and you see that there is a change of signs from -4 to -3.9. So I know that originally we have shown that the 0 is on the interval from -4 to -3, and now we've narrowed that down even more to say that that 0 must be between -4 and -3.9. So I want to narrow it down even more, and so what I'm going to do is change my table set once again. So if I adjust my table set, I still want the table to start at -0.4, but now I want my change in values to be even smaller. So I'll make it 0.01. And let's take a look at the table now. So now my table is incrementing 0.01. Let's get another screenshot of this so we can take a closer look. And once again, we want to use that intermediate value theorem to notice when there is a change in signs. So we can see here there's a change in signs in the Y menu, and that happens on these two values here. So just to recap, we originally started with the intermediate value theorem proving that there was a 0 between -4 and -3. Then we narrowed that down to be in between -4 and -3.9. And now we're narrowing it down to be in between -3.96 and -3.95. So we want to go one more iteration of this so that we can have our 0 accurate to 2 decimal places. And you can see that we already have 2 decimal places here, but we need to know what the third decimal place is to know whether we need to round to have the second decimal place a 6 or a 5. So we're going to do this process one more time. So we have our calculator again. And I'm going to have my chart over there so I know what to do the table set at. And this time I want to start at negative 3.96. And I want to make the change in my values even smaller, so it'll be 0.001. And let's go to the table, and once again we're looking for a change in y values having opposite signs. So let's get a screenshot so we can look closer again. Okay, so now we can see that we have a change in signs occurring right here with these x values. And so now we're going to know what to round to. So now we've narrowed the 0 down to be in between negative 3.952 and negative 3.951. And so since the 0 is in between those two values, we know if we round to 2 decimal places, that 0 would be negative 3.95. Information is given about a polynomial function f of x, whose coefficients are real numbers. Find the remaining zeros of f. We know that this polynomial is of degree 3, and we have identified already 2 zeros of this polynomial function, 5 and 6 minus I. So we're going to use the conjugate pairs theorem to identify the remaining 0. There is only one remaining 0 because of the fundamental theorem of algebra. This polynomial is of degree 3 and will have at most 3 zeros. So we already have 2 zeros, there's only one remaining 0. The conjugate pairs theorem says that let f of x be a polynomial function whose coefficients are real numbers if r equals a plus bi is a 0 of f. So we have a 0 that is a complex number. The complex conjugate a minus bi is also a 0 of f. So what this theorem tells us, as long as we have a polynomial function with real coefficients, if we've identified one complex 0, the conjugate of that complex 0 is also a 0. So we do have one complex 0, 6 minus I, and the conjugate of that 0 would be 6 plus I. So 6 plus I is the remaining 0 of this polynomial function. Form a polynomial function with real coefficients having the given zeros, given degree and given zeros. The degree is 4, and the zeros are 1 with multiplicity 2 and 4i. So we notice that we have a polynomial of degree 4, and the fundamental theorem of algebra tells us that we have at most 4 zeros. So we have a 0 of 1, and it's stated that it has a multiplicity of 2. When a polynomial has a 0 of 1, that means that it has a factor of x minus 1. And the fact that this has a multiplicity 2 means that we have another factor of x minus 1. Then we notice that we have a complex 0. We have a complex 0 of 4i. And as long as our polynomial function has real coefficients, we can use the conjugate theorem the conjugate pair theorem to state that we also have a 0 of negative 4i, the conjugate of 4i. So that means that we have, for the 0 of 4i, a factor of x minus 4i, and for the 0 of negative 4i, we have a factor of x plus 4i. We're going to use these factors to form the polynomial. So our polynomial function f of x will be a. A is an unknown leading coefficient because there are many polynomials that will fit this description, and so we're leaving that value of a unknown. And we have a factor of x minus 1, another factor of x minus 1, a factor of x minus 4i, and a factor of x plus 4i. I'll start to simplify this by multiplying, and I always like to multiply the conjugate pairs together because they form really nice expressions to work with. And I'll also multiply x minus 1 times x minus 1. So that would give x squared minus x plus 1. And if I multiply these conjugate pairs together, that becomes x squared minus 4ix plus 4ix minus 16i squared. I'll combine like terms, and this gives x squared minus 2x plus 1 minus 4ix and plus 4ix cancel each other out. I squared is defined to be negative 1. And negative 16 times negative 1 is a positive 16. So we have x squared plus 16. And then we'll multiply these two expressions together. So I multiply x squared times both of these terms, and that will give x squared times x squared plus 16. And then I'll multiply minus 2x times both of these terms, minus 2x times x squared plus 16. And then finally I'll multiply 1 times both of these terms. That's 1 times x squared plus 16. I'll use the distributive property to get x to the 4th plus 10x squared minus 2x cubed minus 32x plus x squared plus 16. Let's see if I have any like terms I can combine. And I have 2x squared terms, and I'll combine those like terms and also write these terms in descending order. So that's x to the 4th minus 2x cubed plus 11x squared minus 32x plus 16. So we form the polynomial with zeros of 1 and multiplicity 2, and zeros of 4i and negative 4i. So I'm going to come back and make a correction, and I'm going to highlight the mistake that I made here. The mistake that I made was in being a little bit sloppy and copying down my numbers. So I want you to notice right here that this is supposed to be a 16, but as I was sloppily writing it, it looked like a 10. So I need to make this correction. So this number here would be a 16. And that means that when I combine like terms, instead of this being 11, this would be 17, 16 plus 1. So the polynomial function is x to the fourth minus 2x cubed plus 17x squared minus 32x plus 16.